Hello, everybody, and welcome back to Ask Math Anything. We took a break last week because I unfortunately was on the way to Brazil. I might have mentioned that on one of the live streams here that I was possibly going to Brazil, and I went there because the National Math Olympiad camp of Brazil was going on, and they wanted me to say a few things over there. Of course, while over there, I was also doing various other things with the new way of fighting disease that we've invented, talking to people from science and from government. But I'm back tonight. Sorry for the delay tonight. It's because between Brazil and here, I also stopped by Florida, where I just gave some talks yesterday, 2 talks in Florida. But now we're back here for the Ask Math Anything, which is our tradition, where about every week we will discuss anything that people are wondering about math. And the way that this works is that if you have a question, just ask it in the chat. What I will do is I will try to pick questions from the chat that are around the level of what people might be doing if they're doing algebra or geometry in math competitions. And the hope is that we can explain things that will be understandable to as many people as possible while also being interesting. Now, I've actually not seen these questions, obviously, because you're asking them live. And so what I'm going to try to do is I'll choose things that look interesting. I'll try to solve them, and then I'll also cook up some math lessons on the spot to try to explain things in a way that hopefully is somewhat entertaining. All right, so what do we have here? I'm looking around to see what is here. Some people are posting different kinds of questions, and fortunately we have our moderating team, actually it's Debbie, who's pulling questions from the chat when the chat moves too fast. What do we see here? Oh yes, that's right. So there was one question that was asked that I should talk about this time because we delayed it from last time, and so we'll definitely do that. But let me start with something simpler first. I see that there's a question by Max Quo. Why is the product of the slopes of 2 perpendicular lines always -1? Always -1. Let's start with that. For that, let's pull up the board. Here we go. Right, so let's just start with that because that is a relatively nice way to just start this live stream. And the question is, suppose I've got 2 perpendicular lines. Why is the product of the slopes -1? Well, the easiest way to think of that is that let's draw 2 perpendicular lines first. This one. Sort of perpendicular, not really lines. Just a second. Oh, because I just came back from Florida, one of my pieces of equipment is over there in the other side of the office. I'm just going to grab it. I'll be back in 5 seconds. Hopefully that was 5 seconds. Here we go. Bam. Okay. Now let's try to draw a proper line. You guys make it so that I have to keep my exercise up. Okay, great. I've got 2 perpendicular lines here. And now the question is, what can we say about the slopes? Well, here's the easiest way to think about it, right? What's the slope anyway? The slope is how much you go up divided by how much you go across. Okay? It's usually written as the rise over the run, where what you do is, you have some kind of a line, and then there's a rise, which is how much you go up, and how much you go across, which is the run. Okay, so now if I go and look at this picture, I can actually see that these perpendicular lines can make some nice pictures. For example, if I look at the slope of one of these lines, here's the rise. Is that going straight down? Sort of. Let's do this. This is supposed to be going straight down, and then it's going straight across here. So there's a rise on this side. And just for me to be able to talk about things with different colors, I'll call this one the run. Okay? But now I did this on purpose. Because if you look at these lines are perpendicular. Okay? And so since they're perpendicular, it happens to be that the angle here is 90 degrees. It's a 90-degree angle between those 2 lines. Well, over here I've got a little narrow angle in the triangle. And I have a big angle in the triangle. And I have a 90 degrees here also. So what that means is that these 2 angles add up to 90 degrees. That's because the sum of all 3 angles is 180, and 90 of them are eaten up over there. So these 2 add up to 90. Oh, but this tiny thing and whatever that is also adds up to 90. That means that what's left here is equal to that little angle, that big angle over there. Okay, so then if I draw another triangle like this, okay, where that's a right angle also. That doesn't look quite straight. That doesn't look quite flat. Let's do this again. Okay, draw that there. Well then, it turns out that this little angle and that little angle are the same also. Okay, so what I've gotten is that this angle is the same as this angle. And I also have the 90 degrees and the 90 degrees. I have some similar triangles. That's what I'm trying to show. So that means that whatever this triangle is, its ratio of stuff is the same as the ratio of stuff over there. But now it becomes interesting, because what is the rise and the run ratio for this pink triangle? If you look at it, the rise and the run ratio for this triangle, which is here, is going to be exactly 1 over the rise over run ratio of the other triangle. Do you see that? It's because you basically are flipping which one is the horizontal and which one is the vertical. The thing that was the vertical here over on the other one becomes the horizontal, and whatever was the horizontal here over there becomes the vertical. The key is that these two are what are called similar triangles, and therefore the rise over the run of one of the triangles is exactly the flip of the rise over the run of the other one. And that's it. So that's why the product of the slopes is 1. Wait, no. It's -1. And why is it -1? It's -1 because over here, this is not quite a rise. It's a unrise. It's a drop. It goes down. The key is that the sign flips, the plus or minus sign flips, because one of them starts going down instead of going up. So that's actually why the rise over run for each of these two lines multiplies together to be -1. It's because if I didn't care about the plus or the minus, then I'm just flipping which is the horizontal and which is the vertical. Okay, so that was this quick question here. Let's now do some other questions. So let's go and play with the next one. And the next one is, So let's go and do this one, which we had promised that we were going to try to think about last time. And this one might take us a while now, because I don't know how to do it, okay? So the question says, suppose I have triangle ABC, and I have some medians, okay? So here's a triangle, ABC. We're going to have a triangle. Here we go, ABC. And we have some medians. Median is where you, well, in order for us to see that, we should probably draw this all the way over there. A median is where you connect the middle point of the other side to each vertex on the other side. Okay? So I have these medians. And now the problem says that the medians have certain lengths. One of the medians has length 12, and the other median has length 15. So one of these is 12, the other one is 15. And the question is, what's the biggest possible area of the triangle? Okay. So one of the useful things about triangles is that if you draw these medians, they actually trisect each other, in the sense that whenever they hit each other, it turns out that the ratio of this side, this piece to that piece is 1:2. This is actually something we might talk about in a geometry class, but I won't go deep into that now. Maybe if we have extra time, I can show you why that's true. But let me first see whether or not that's useful, okay? So since I know that the medians are 12 and 15, because of the trisection, this one would be 4 and 8, and the 15 would give me a 5 and a 10, okay? And what I'm saying is that if this turns out to be a fact that's actually useful, well, at the end, maybe we can talk a bit about why this is actually true. Okay, because I'm still trying to understand the question to see, how do you do something like this? Well, now the thing is that I've got some medians, okay? And I want to know what's the biggest possible area your triangle can have. So that means that I need to know the relationship between median lengths and triangle area. As you can see, I'm just thinking first. Oh, cool. I'm just playing around in my head. I don't know if this is possible, but I look at this picture, and the first thing I say is, you know, I don't really know much about areas of stuff, except that I know that if I have a quadrilateral where the two diagonals are at a right angle, that makes a very big area. Oh, I think I can actually solve this problem. Okay. Yeah, so somebody's suggesting, by the way, Jesse Guo, it's a good idea you're suggesting, draw the third median. That might work. And fun fact, if you haven't learned this before, if you draw the third median, it will actually go right through that point also. It's really neat. But there's a reason why I'm doing this particular line here. It's because, actually, it turns out that since these two are the midpoints of the sides, then there's actually a known ratio between the area of this triangle and the area of this quadrilateral. Okay? And that's because I've just cut these 2 points off at halfway. Scale factor of 2, somebody said. It's a similar triangles. Yes, Jesse Guo, you're right. This triangle here, if you scale every side length by 2, poof, it becomes the whole thing, right? Because this thing scales by a factor of 2 and flies over there. This one scales by a factor of 2. I'm scaling away from this point. It flies over there. And so this triangle here, if I scale by a factor of 2, becomes the whole thing. Okay, let me write some letters just because I'm feeling like we're on the right track now. So I'm going to write some more letters, D and E. Okay, and the reason I'm writing that is because I know something about the ratios of triangle areas. I know that the area of CDE, that's a triangle, is exactly equal to 1/4 of the area of CBA. And the reason is because if I just scale it by 2 in each dimension, it's a 2-dimensional picture, so it's going to scale by 2 squared, which is 4. All right? So that means that this CDE is 1/4 of the whole area. To make it look a little bit more pretty, I guess we could just do this. Looks better, okay? But now, if this is 1/4 of the whole area, what is the fraction of the area which is the quadrilateral? Well, that's 3/4. That's 3/4. And I already see. Jesse Guo, well said. So basically, we just need to find the largest possible area of DEC. So I don't quite want that. What I want to say is, I'll have a ratio between these two areas, and the question will boil down to trying to find the biggest possible area of this quadrilateral. It's because if the area of the triangle is 1/4 of the whole thing, then the area of the quadrilateral is 3/4 of the whole thing. So the area of the quadrilateral, A, E, D, B, is going to be 3/4 of the area of the whole triangle, CBA. Okay? Whenever you write down the labels of a particular shape, you need to make sure you kind of go around in a consistent way. So that's why I wrote this as AEDB. You can't just be like, oh, AEBD. It has to go around in the same way. Okay? But now, once I've gotten this, I can say that if I knew what was this quadrilateral's area, I can get the entire triangle's area out of it by just multiplying by 4/3. And that's the important thing. The question was asking, what's the biggest possible area of the triangle ABC, or CBA, however you like to think of it. So because I had the 1/4 and the remaining part was 3/4, now I flip it over, and I find out that the area of the triangle CBA, which is the ABC, or however you like to call it, that's equal to 4/3 times the area of AEDB. Okay, so now this is just asking me, how can I make the area of the triangle biggest? Well, let me see if I can make the area of the quadrilateral biggest. If I look at a quadrilateral, and I have these two diagonals, now how do you make that the biggest possible area? So if you look at what's going on, I have a quadrilateral is actually made of, I can think of it as 2 triangles. I'll start by thinking of it that way, okay? You might say there's 4 triangles here, but I'm going to look at it as 2 triangles. The blue one and the pink one, okay? So I have these 2 particular triangles, and I'm already seeing Jesse Guo is thinking, probably BE perpendicular to AD. Yes, exactly, that's what we want to do. And the reason I'm looking at it this way with these particular triangles is because once you have a triangle, like this blue triangle up here, well, I know the base of the triangle is 8 plus 4, which is 12. how do I make that triangle have the biggest possible area? Well, if the base is stuck at 12, I want the area, I do want the area as big as possible, but I want the height to be as big as possible. Well, from this particular point right here on this base of that blue triangle, I have to go out by 10. How can I make it so that that point is as far away to make as big a height as I can for this? Well, I should make it perpendicular. So the key is that if I want the biggest possible area, since I have this 8, 4, think of it like we got some sticks, right? You got some sticks moving around. And if I want to think about where I can put that point A, well, from here it has to be 10 away. So there's this whole bunch of places you can put A. The way you make A so that that A is a height that's as far as possible is to make it perpendicular. And it turns out that perpendicular also makes this one as far away as possible. So that's exactly why the answer would be, if I could make these two to be perpendicular, then I'm in good shape and I'm done. Okay? So what I've just found out is that the biggest possible area that I could ever get for that particular quadrilateral would be if I just made perpendiculars. And then I can actually get, some area of that thing with a bunch of half base times heights. Before I do that and say perpendicular is the way to go, I should also know whether or not there always exists a triangle where the medians actually do look like that. Is that actually possible? So I'm going to take a detour first and say, well, if I know that I've got this 12 and 15, is there definitely a triangle where those things are perpendicular and they are the medians? Let's find out. To do that, I need to reverse the construction. Actually, I need to do a construction, okay? So now let's think of these sticks. That's how I was thinking of it before. I have one stick, and it has an 8 and a 4. And I have the other stick, which has the 5 and the 10. Right? And now what I'm going to do is this time I'm going to very intentionally just cut the 8, 4 thing, where it was supposed to be, and also cut it in a way where, yes, I go exactly 5 perpendicular this way. Maybe that's 5. And I go exactly 10 perpendicular this way. My lines are kind of wiggly. Okay, so that's 10. All right? Now, my question is there definitely a triangle where these are the medians? Now let's try to make the triangle. If I wanted to make the triangle, one of the vertices has to be up here. Okay, and another vertex has to be here. These are two vertices of the triangle. So let's just go ahead and connect them. The next thing that I need is that I need that somehow, if I made this guy go all the way across, oh, this is tricky now. Now I'm not even sure this works. The reason is because if I really want these to be medians, I would actually need that this thing, if I go all the way across, and this one, if I go all the way across, it just so happens that these are equal and that those are equal. Is that definitely true? This goes across, and this goes across. You see, I'm trying to say I don't have much choice right now. If I force that to be that point right there, and if I force this to be this point right here, if I make it so that this line has to go through that, and this line has to go through that, all right, but are they medians? In order for them to be medians, I better have that these two are equal, and these two are equal. We might be in luck, though. I wonder if we can use some more kinds of similar triangles. Oh, this is so cool. Yes, we can. It's going to work. All right. So the thing is that when I drew this thing at first, I was like, oh no, this looks terrible because these aren't equal and those aren't equal. And if that's the case, then I'm dead. It doesn't work. This is not actually a legitimate pair of medians. But you see, here you can actually do it. The reason you can do it is because it turns out that I just drew my diagram in a not to scale way. If I look closely at what's going on, here's a 10, here's an 8, and here's a 5 and here's a 4. They have the same ratio. 10, 8 is the same ratio as 5, 4. Cool. And they both have a right angle in between. That means I have another set of similar triangles. It means that because this 8 to 10 ratio is the same as the 4 to 5 ratio, well then, I have that these two triangles are similar to each other. Sorry, it's because the ratios match, and they also have an angle in between. This is called Sas Similarity. So I have similar triangles. This triangle and that triangle are similar by Sas. Let's give some names. what were the names? A, B, E, D. Okay? So this is A, this is B, this is D, this is E. We need another name. Let's put a letter here called G. G, by the way, is the letter that you usually use in geometry to denote the center of mass of a triangle. And that's actually what this is. That's why I'm using G. Okay? Let's keep going. So the important thing is if I look at these two triangles, I have some Sas similarity. And that's triangles A, G, B. Let's draw a triangle sign because I think that's what most people do in school too. Triangle A, G, B is similar to triangle D, G, E. Everyone with me so far? I get these two similar because the ratios on each of the triangles around that particular angle are the same. And also that angle is the same on both. Oh, cool. Calvin says that you're taking a geometry class and you just talked about similar and congruent triangles, including SAS. All right. What about F? Oh, yes, Tony Master is asking, why don't I have F? The reason is because actually when you draw like a lot of these things with triangles, usually what you do is that you do A, B, C. You usually make the D opposite the A, you make the E opposite the B, and you normally save the F to be opposite the C. And for whatever reason, G is usually the center of mass of a triangle, which is what you get when you intersect the medians together. So that's just why I wrote the G there. But now, why am I doing this? I'm doing this because now because of the similar triangles, I have some congruent angles, right? If I go and mark some angles, like this one. Here's an angle. This is an angle inside the AGB triangle. And the AGB triangle is similar to the DGE triangle, so that angle at the D is congruent to the angle at the A. Does anyone know what this lets me know? I get to say something pretty cool about the picture just because of these two similar triangles. Actually, just because of these two congruent angles. Since that angle and that angle are the same, I know something very nifty about these lines that I've drawn. And it even looks that way in the picture. They're parallel. It's because if you have a line in between and you have congruent angles on each side, then you have parallel. This is going to be very powerful. So they're parallel. But there's more that I know. I also know their ratio. If I want to know the ratio of how you scale from the AGB and turn it into the DGE, what do you multiply by? This is not really what you write in school, but I'm just going to write it like this because I think you understand what it means. You multiply by half when you go from the AGB to the DGE because it's like 10s become 5s and 8s become 4s. Aha! And, oh, somebody's saying, didn't we already know this because it's a mid-segment? Actually, we don't. The reason I'm doing this part right here is I was curious. If you just go and write these sticks, this stick of length 12 and this stick of length 15, and you make them intersect right there, is there a triangle for which those are medians? I don't know beforehand that it's going to be medians. Because, like, what if it turns out that when you put them down and then you finally build the whole triangle, it's like, oops, it's not a mid-segment, right? So actually, you're right that it's matching the midpoint theorem, but I'm actually going backwards. I'm trying to say, the question only told me, I got these two medians and I have the lengths. And I don't actually know that every way of putting these always makes them actually legit medians of a triangle. And so what I was trying to do is I was trying to be like, okay, fine, I'm going to put the two down. Let me try to build a triangle where those are there and hope that they're medians. So right now I'm trying to prove that they're medians. And so I'm just finding out that just because I drew them this way and I intersected them at that point, magically, and that's actually why it's useful, this 1:2 split. This is called a trisection point. Just because of this split, poof, I get parallel lines. But once I know they're parallel lines, and I also know that the ratio of the lengths of the parallel lines is 2:1, then I have another set of similar triangles. And that's how I'm going to get that E and D are the midpoints. So it's all going to work. You see, let's call this point C. Once I have two parallel lines, we get to do more similar triangles. except this is AAA similarity, angle, angle, angle similarity. We're going to get that this let's say CDE and CBA are similar. These are AAA similarity. Ah! So I now get CDE is similar to my head. Let's do it over here. Triangle CBA. Okay? So because these two are similar, then I know they're similar because of AAA. They share the angle at C, and I have the angle at the E is the same as the angle over here at the A because of the parallel lines, and so on. Yeah, similar to my hair. Okay, but now once I've gotten that these are similar, well, I know what the ratio is between them. When I go from this CDE to CBA, the ratio between them is also this 1:2. And it's a 1:2 because I know the ED and the AB have a 1:2 ratio. So if I was going to say, what happens if I go from one to the other? CDE to CBA, actually I'll write that's a times 2. Over there I wrote it's times a half because that was from the bigger to the smaller. Here it's from the smaller to the bigger. But this is perfect because if I know that it's a times 2, the times 2, by the way, I got from that one. It's because of the times half, so I know this is times 2. Bingo! Now I know the sides have to be in the ratio of 1:2. And that's what tells me that the CE is exactly half of the CA. CE is equal to 1/2 of the CA. And that's great, because that means that E is a midpoint. And then, since E is a midpoint, well, then this is actually a median. BE is a median. So this implies E is a midpoint. I'm excited, so I'm writing an exclamation point. Okay? And similarly, over here, I could do the same logic, and I could get that D is a midpoint. Using the same logic. Maybe I'm less excited, so I didn't write an exclamation point this time. But okay, so in that case, I've just found out that if I do write these two lines and cross that way, then poof, they will make a triangle. It'll make a triangle, and they will be the medians of the triangle. That's cool. That is so satisfying. I'm satisfied. I hope that you're talking about this thing too. Make sure that it's not interpreted as a factorial. Yes, if you ever want to write some number with an exclamation mark after it, make sure the number is only 1. Because that way, even if it's a factorial, it's still right. Okay, but let's see. So now I know, actually, what this is super cool. I didn't even need that they were right angles to show that I can always make a triangle, for which those are the medians. Actually, what this shows is that if you just take any two sticks and you make it so that they trisect each other, they cut at the points where you have 1:2 ratios, no matter what angle you pick, if you finish out the triangle, those will be medians. Cool. But now I can go back. Let's see. Well, I want to just take 4/3 times the area of that quadrilateral. And the biggest possible area is where I put the right angle. Okay? That's what we were doing. And so in that case, I'll write then that's maximized max area of CBA is then equal to 4/3 times the area of the AEDB. Now, the area of this, it was half base times height for the top triangle, half base times height for the bottom triangle. I'll do it slowly, and then we'll see a neat thing happen. So the slow way to do it is 1/2 times the base. The base is 8 plus 4 is 12, times the height is 10, plus another half, same base, 12, height of 5. But I'm going to also write that as 4/3 times 1/2 times 12 times 10 plus 5, which is 15. Okay? And what I've just done here is I just said, well, if I have half times 12 times something, and half times 12 times something else, the distributive property lets you just add together the 10 and the 5. And this is actually a formula I've seen before. It's that if I have a quadrilateral, and if they have a right angle if the diagonals make a right angle, then the area is just 1/2 of the product of the diagonals. Fun fact, actually, another way to see this, if you wanted to know, is you could draw another quadrilateral. It's actually a rectangle around all of it. And if you did that, if you imagine where my finger is going, if you did that, then what you'd find out is that each of these triangles has another triangle outside, okay? And so actually this quadrilateral is just 1/2 of the area of that rectangle thing would make, which is exactly the rectangle with length and width of the 12 and the 15. All right, but now let's finish up because the question asks for the answer. So I just need to know 4/3 times 12, 4/3 times 1/2 times 12 times 15. Let's go do some canceling. I can take a 2 out of there. I can take, oh, let's take a 5 out of there. I did it this way because I see a 2 and a 5, which multiply to 10. That's easy. So I have a 10 times 12, 120. And we're good. And I won't write an exclamation mark after it because then that would be a factorial. Okay, so that's it. So the answer is 120. All right, how are we doing on time? Because, okay, it's 8:51. I'm able to go for, let's see, about 14 more minutes or so. And so I did promise you that I would explain something about my insight of like how, not my insight, the classical Greeks' insight of like why these medians happen to cut each other at this ratio of 1:2. That's actually kind of nifty. I'll explain it real quick, okay? Although one thing that you may have seen from this part is that it's actually quite useful in that if I just start them with the 1:2, I can always make a triangle where they're medians. But if you want a quick explanation of why is it that if I take any old triangle, any triangle, and then I go and draw these medians, okay, they all cross each other, and it turns out that they all split at the ratio of 1:2. Why is that? What's the easiest way to do this? I'm thinking to myself, oh yes, okay, I see the easiest way to do this. Actually, I didn't know this before. It's not like I come in already remembering everything. I just look at everything and try to figure it out. Let me explain why these cut 1:2, and it's actually just going to reverse the logic we just did when we made them 1:2 and got triangle. I got them as medians of a triangle. See, suppose I drew two medians, okay? Well, because I drew two medians, using the same logic we had before, let's label these, sorry. A, B, C, D, and E. Let's draw that line from D to E. Well, now that I've drawn this line from D to E, look, this is something where I have, yes, where each of them are half, okay? Excellent. So what I have here is that this D is a median, sorry, D is a midpoint, so this CD is exactly half of CB. And CE is exactly half of CA. I have SAS similarity for the triangles, this small one here, CDE, and the big one, CBA. Okay? So the first thing I get is SAS similarity gives me that triangle CDE is similar to triangle CBA. And that was because the sides, the ratio of the sides is that somehow each of them was 1:2. And 1:2, and they have a common angle in between. Poof. Once I have that, then the angles are all going to match up. And so that's what tells me that this angle here is the same as that angle there. The angle CED is the same as the angle CAB. But now I see a line and two congruent angles, and that forces that I have parallel lines. Okay? Once I have parallel lines, I can say something else about some other angles also. I can also say, this is also just something generally true if I have these nice parallel lines, then whenever you draw this kind of an X shape, it turns out there's a whole bunch of angles which are all congruent to each other. So in particular, when I have these two parallel lines, well, I know that this angle, which I'm marking with two ticks, two pink ticks, is the same measure as this angle here. And that's because I had parallel and parallel. So this thing here that it makes with this line in between is the same as that angle there. Great. The same is true on the other side too. I guess I need to draw 3 tick marks now. Thank goodness for colors. This blue angle and that blue angle are the same. Oh, But now I have two angles and two angles there, which are also matching each other. And of course, these two angles which are in between, they're going to be congruent as well. But in general, if I have a pair of triangles and they already have two pairs of angles that match, the third pair has to match because the angles all add up to 180. But that gives me AAA similarity. So I get some triangles, which I need to give a name of a point. Let's call this G, right? I have some triangles. You can see I'm basically going and doing the logic the other way around. So what I have here is that the triangles, well, let's just call it ABG and DEG are also similar. ABG similar to triangle DEG. Why did I do all this? I did all of this because I want to say something about the ratios of these bits. I want to say that this is half of that. But here's why. Oh yes, that's right. AA works too. I see that this is in the comments. AAA or just AA. Because once you have AA, the third A follows. It's like once you start screaming, you don't know how many A's there are in the scream. Okay, but now the CDE, CBA, from the first thing, what's the multiplying factor? Well, if I go from the CDE to the CBA, well, I know that the multiplying factor was blowing up by times 2 because it was blowing up by times 2 on each of these. So that's how I already knew that the DE is half of AB. Okay, so over here, I already knew that the DE was half of the AB. That's great, because the DE shows up again in this pair of similar triangles in the second line. So the DE is here, and the AB is there. That means that this other pair, ABG, going to DEG, that's also going to go with a 1:2 or 2:1 ratio. And from the bigger to the smaller, it's by times 1/2. And that's why these medians cut each other at these points where one part is double of the other part, you see? Because this similar triangle thing, what are the corresponding parts? The corresponding parts are like this part, BG, corresponds to EG. So it's actually this part and that part across from it that is a 2:1 ratio. And then here, this is also a 2:1 ratio. So that's it. So that's why these are trisecting. Trisecting means that they cross at the point where that would be if you wanted to cut it into thirds, meaning that, well, the other trisection point is here. But that is exactly why when I look at this is to this, it's going to be 2:1. So that's one way of explaining this. Oh, fun fact. Once you know this, this actually lets you know why the third median goes all the way through also. Because you see, if every time two medians intersect, they cross over at the place where they cut it 1:2, well, look, if I drew this median B to E, BE, then it's going to cross this median at the 1:2 point. Good. Now pretend this is gone. If that's gone, and I draw the median this way, it's going to strike through this DA thing again at the place which is 1:2. That means that they go through at the same point, actually. And so that's one way of proving that these three medians all will intersect at the same place. They will all intersect at the place which is exactly 1:2 along one of the medians. Okay, that was fun. So this is why when this question was asked last time at the end of the live stream, I was like, it seems like a rich question. I don't know how to do it, but it seems very rich, and I want to make sure we dedicate enough time to solve it, not just like 5 minutes. But at the end of the day, we find out that the answer is, it's actually quite nice of a problem. Just make those medians perpendicular, and you're done. Okay, let's do more problems. How much time do we have left? We have like 11 minutes. No, we don't. I can't do math. I mean, I can't do arithmetic. We have like 5 minutes. Okay. Whoa, so many good questions. All right. What I'm going to say is, Debbie, thankfully, is helping to watch all these questions. If we do find other great ones, we might save them for later too. But let's see. Wow. Okay, somebody has an interesting point about 3 to the power 4 to the power 5. Is the product of two integers. What? Really? So somebody said if you write 3 to the power 4 to the power 5 plus 4 to the power 5 to the power 6. They're telling me that this is the product of two integers. Each of them is bigger than 10 to the power 2002. I'm not sure I see a nice way to do this question, because that has to do with trying to find a way to factorize this. And this is not a form that factorizes nicely. So I'll say I don't know how to do your question here. When I say I don't know, it's like, it seems like it might have some brute force, and it can't be brute force. You can't use brute force for numbers this big. But yeah, I'm just looking at the chat to see if anyone puts things here. Yeah, I don't see a short explanation for this, because in order to be able to factorize this, I would need a nicer form. Oh, do I have a nicer form? 4 to the 5th and 5 to the 6th. No, but they don't have common factors either. I was going to be like, if they are both like cubes or something, you can do factorization. But they're not cubes. It's a 4 to the 5 and a 5 to the 6. Oh, wait. Oh, wait, no. I was going to try to use the 4 and be like, well, 4 is 2 squared. But that's not nice, because I have some sum of 4th powers. Well, can you factorize sums of 4th powers? Maybe you can. Or maybe not. Yeah, so I don't see anything quite nice here. I'll say, like, for this, that's why we have Mathematica. Well, actually, it's pretty big. So Mathematica is not going to be that fun here, because we can't really prime factorize this just with brute force. I was trying to see, are there any nice formulas that you can break this apart into? Just letting you know what was going through my head. It's like, I don't know if you've seen this before, but if you have x cubed plus y cubed, it actually factorizes. Why did I write parentheses? I'm not sure. This always factorizes. This is equal to x plus y times x squared minus xy plus y squared. Super cool. If you multiply it out, you'll find that out. But now, that would be great if I have something like cubes. The problem is I don't have cubes. I have like 2 powers of 4 to the 5. So it's like very even powers. Actually, 4 to the 5 is a power of 2. So I don't actually see a nice way. Wait, what's Sophie Germain? Yeah, Sophie Germain is another one of these factorizations, but I don't see a nice way to factorize just like something to a power plus something else to a power. I might be more excited if they were both like to the power 5. Like if somehow both of these exponents had like a 5 in it, then I'd be like, oh, we have things. It's like sums of 5th powers. There's another version of this kind of a thing where there's fifth power things. But for even things, I don't actually have a nice one. It's like a difference of squares that you can do. If you have a sum of squares, you need to use I, the imaginary number, to do a nice factorization. So I don't have something for you on that, unfortunately. And somebody says the answer to this equation is the 9,408 digit number. So I'm afraid I can't do this one for you. I can't do every question that comes sometimes, but I did want to try. It is powers of 5. Are you sure? No. Oh, that's something else. Okay. Other questions that we have here. Maybe we'll use, since we're down to like 2 minutes, let's do something more philosophical, right? Okay, yes, somebody's asking a question about math competitions. Let's just do that. That would be a great way to end. Because the person is asking, Kaladin Stormblessed says, if I am in 6th grade and doing AMC and math counts, should I try and mock as many as possible or save some for later years? There was once, I was at the Math Olympiad training program as a student. Once I was there, I think it was my first year as a student at the national training program. And there was something on the calendar, like there was some calendar of events of all of these different things that you'd be doing on the different days of the week. I don't know how many things I drew here. A week does not have 6 days. But anyway, something like this. Let's say 5, okay? And then it was telling you what would be happening on various days. And at some place, it said this. IMO is the International Math Olympiad. And there was one student who said, why would we want to mock the IMO? The IMO is the International Math Olympiad. Why are we all going to, for this hour, just sit there and mock the IMO? Oh, well, actually that's a mock test. So mock just means it's a simulated test. So the question that the person was asking was, like, if you want to prepare, should you just try to mock as many as possible? Don't make fun of the test. But if you want to go and practice a bunch of them, that's okay. Although I would give the advice that if you are trying to get better at these things, don't just do all the problems, because some of the problems will be fast and easy. Some of them will be hard, like really, really hard, where you have a lot of trouble doing them. And some will be kind of in the middle, where you can kind of do it, but you have to struggle. So what you should do, really, is you should just put your energy on the ones that you have to struggle. So maybe don't spend so much of your time practicing easy early questions, if they're easy for you. And don't spend too much of your time trying to do a question that you have no chance of solving. But just work on these middle ones. And then as you get good at that, you'll find that the ones that are just on your threshold of what you can solve get harder and harder and harder, and you just keep working there. So I guess that's what I would advise. In general, whenever you're learning anything, just keep trying to do what's hard for you but not impossible, and you'll find out you get better and better. With that, unfortunately, that's the end of our live stream for tonight. Next weekend, I'm actually not going to be here to do it, but the weekend after that, I will be. So I'll see you back at that time again. Then that will be in 2 weeks from now. Good night.